and then I would like to share content. So I will continue the lecture on mechanical behavior of bone. Basically from where I left yesterday, the theory of bone remodeling. Hello. Can you see the slide?
Yes, sir.
Yes, sir. Yes, sir.
So everything is fine. So I'm now moving on with the presentation. Okay.
Yes, sir.
Now, as we discussed yesterday, that a change in the mechanical environment, we are taking an example, a gross change in the mechanical environment is induced by implantation. Okay, so implants may be very elementary implants like plates and screws up to joint replacement. Now, this implantation causes change in mechanical environment within the bone structure, and this gross change in the mechanical environment triggers structural and morphological change in the bone structure. That is exactly what we summarize as bone remodeling. Now let us move towards from theory of the bone remodeling to the simulations. Okay, so first we actually discuss about the theory and then how this theory is implemented in the computer simulations which predicts bone remodeling. That will be discussed. Okay, so bone remodeling, the adaptive bone remodeling is basically a time-dependent phenomenon. Okay, as you all would understand that with time, it actually the bone structure evolves through alteration in mechanical environment. So the bone basically adapts its structure with the altered mechanical environment by two processes. One is bone resorption, that is triggered by activity of osteoclast. Bone resorptions mean bone loss, very grossly. Rather, it should be more precisely stated as reduction in bone density, bone resorption. And the other activity is the bone apposition, which is triggered by the osteoblasts. Okay, bone apposition, A stands for addition, so it is increase in bone density. Okay, so this process of continuous process of bone resorption and apposition due to activity of osteoclast and osteoblast respectively goes on until the structure reaches an equilibrium state. Okay. However, as I told you earlier, the altered mechanical environment, due to the altered mechanical environment, bone adapts to structure, but it always strives to reach the natural situation. Okay. It strives to reach the natural situation, which is considered to be a state of equilibrium before the surgery. So the phenomenon of bone remodeling explains the response of bone tissue to a significant alteration of its stress-strain environment. When we say mechanical environment, we mean that it is a stress-strain environment. Okay. Now we have two important variables here, as you can see. One is S, another is SREF. Okay. Now SREF refers to the reference stimulus. Just a moment, pointer. So SREF is referred to as reference signal, and this reference signal you can obtain from the intact femur. What is intact femur? It's the natural femur, not operated. Okay, so this is an equilibrium state, and this is the reference signal based on which bone tries to remodel the structure. So we refer it as SREF. Okay. Now, what is the remodeling signal? This is S is the altered situation due to implantation. Okay, or any other external perturbation. So S refers to the remodeling signal, and this is after surgery. Okay, now what we do is basically the difference between S and SREF, the difference between the two signals is related to bone loss or gain. Okay, this is the main concept behind the formulation of the theory of adaptive bone remodeling. Okay. Now, what is this S? We are referring to as reference signal or remodeling signal. So we actually, S is the strain energy per unit of bone mass averaged over the loading history. Okay, so if you actually apply loading that represents average daily activity, you have to calculate for each load case the strain energy density or the strain energy per unit of bone mass and then average it. So basically, you can see that it is with the number of load cases, N is the number of load cases. For each load case, you calculate the U, the strain energy, and then divide it by the apparent density. So this will give you actually the measure of the S. So UI by rho. So if you have a finite element model of the bone, so each element will have, in the finite element, each element is supposed to have a apparent density value, and each element will have a strain energy value due to the loading, say a particular loading condition. Okay, so UI by rho corresponding to one particular load case, you can calculate. Then you can have n number of load cases. You keep on calculating for each load case, and finally you average it, which gives you the basically the S value. And whether so, in case of the implanted femur, it will refer to as the remodeling signal. In case of the intact femur, it will refer to as the reference signal. This is basically known as the mechanical stimulus in other terms. Alternatively, it is also known as the mechanical stimulus. Okay, and this was proposed long back by the famous group of Rick Heiskus, Harry Wainens, and Van Rietbergen. Okay, Rick Heiskus was incidentally the editor of Journal of Biomechanics for more than 30 years. Okay, he is regarded as one of the most prominent figures in the subject, but sadly, he died a few years ago due to Alzheimer's disease. But he has led a huge research group which has been recognized as one of the most respected research groups in the world. Okay? And incidentally, he was also my PhD examiner in the Netherlands. Now, if you refer to this figure, as I told you, the rate of bone remodeling or the remodeling rate is directly proportional to the difference in the stimulus or the remodeling signals. One is S and other is SREF. Okay. Now, if you look carefully into the figure, that we have the SREF on the x-axis, but there is a zone which is known as the dead zone, where you can see that there is neither apposition nor resorption, no bone loss or no net bone gain. So a dead zone in this figure means that there is no remodeling, either in the form of loss or in the form of gain, in this particular zone, which is plus minus of the SREF. So that means bone doesn't react to small deviations in the reference stimulus values. Okay. Now, in human, it has been observed that this plus minus zone, the dead zone, the range of the dead zone is about plus minus 75% of the reference stimulus on both sides, you can see. So bone doesn't react to small deviations from the reference stimulus. But in case of dogs or animals, it has been seen or observed that the dead zone may drastically reduce to 35% of the reference stimulus. Okay, because the animals generally react far more greater way than the humans. Okay, so the reaction level is always greater, far greater than human. So these things have come up through observation, different experiments, and finally what people have agreed upon is a value of 75% plus minus on both sides of the SREF is a zone which can be designated as a dead zone or a lazy zone. And in this zone, the bone cells doesn't react too much, okay, to trigger a substantial bone remodeling. Okay. But the zones beyond the dead zones on the left and right are the active zones. Okay. Now, if this S value, look at the laser pointer, if the S value is greater than the SREF value, okay, that means S minus SREF is a positive quantity. Okay. So if it is a positive quantity, then it will trigger actually increase of bone density, that is bone apposition. So any positive potential of S minus S, potential difference, would trigger a positive way of increase in bone density. However, on the other side, if S minus SREF is negative, then it will actually trigger decrease or reduction in bone density, which is known as bone resorption. Okay, so this thing goes on continuously until, as you can observe, that the values of the mechanical stimulus fall under this zone. Okay, so as bone structure remodels itself and it strives to reach the SREV value or the dead zone values in the dead zone, this will go on until the values of the mechanical stimulus falls within this zone. That means no net bone loss or gain occurs any further. Okay. Now in this graph, there's another thing that should be observed is you see this is a linear relationship. Okay. The linear relationship is more or less accepted, but theory of bone remodeling proposed by the Rahaiskas group have also argued upon two things. One is that the bone resorption and bone apposition may also follow a polynomial relationship. Okay, may not be purely linear. And the most importantly, bone resorption occurs, at a faster rate than bone apposition. Okay, so they came up with not only linear relationships, they also suggested that a relationship with powers of different powers may be applicable for the rate of apposition and rate of resorption. Okay, I'll show you a little bit later about the relationships. So, as mechanical engineers and scientists, we always try to quantify everything in form of a mathematical equation. So the process of bone remodeling actually can be expressed in form of a differential equation. Okay, so you can see here that we have the terms that the rate of bone mass can be expressed as the difference of S minus, so this is basically one limit of the dead zone. So this is basically here. Okay. So S minus small s is basically the limits. And of course, if you forget about the limits, then it is S minus S ref. Okay. So we introduce the limits here and the range. And so it becomes a little bit different from S minus S ref. So we introduce this term here. So this is valid. So first equation is valid. This is the zone, which is, sorry. Yeah, no. This is the first zone, the resorption. So we have S minus S ref, but this is on the left hand side. So here S is less than equal to this. So this is the zone that refers to the first differential equation. The next part, dmdt is equal to 0. So when it is well within the limits of the dead zone, there is no change in the bone mass. Now here, we say bone mass because here there is no change in volume of the bone, only change in the apparent density. Okay? So ultimately, what happens is change in apparent density will actually result in change in bone mass, keeping or assuming that the bone volume remains constant. And the third equation, dmdt, refers to the furthest zone, as you see on the laser pointer. This refers to the apposition case, when S is greater than the higher limit of the dead zone. 1 plus S into S ref. This is small s, this is capital S. Now all these equations, first three equations, I would not show you now. Let me go back. These three set of equations refers to changes in bone density, that means internal bone remodeling. Okay, these changes in the bone, internal bone structure. The next thing that comes is the external bone remodeling. So as I was telling you, that it follows almost the same rule for the external bone remodeling, but remember, there the thickness of the cortical layer is actually changing. It may increase or decrease. So here it is dx dt, where x refers to the thickness of the cortical bone. So that is basically change in dimension of the cortical layer. And internal bone remodeling is basically change in the apparent density of the bone, assuming the bone volume remaining constant. So if V is constant, then d rho dt is change in apparent density that triggers change in the bone mass. So this is change in density. So what the equation basically transforms into, the internal bone remodeling case, for the internal bone remodeling case, the equation transforms into d rho dt. Okay? And of course, you can see these terms which have been discussed earlier. So I have assembled it in plus minus form, so we can express it like that. But there are other terms, as you can see here on the left-hand side, tau, A rho, and V. Okay, V is of course the volume of the bone element. But what are these terms? So these are certain constant terms that influence the rate of bone remodeling. Okay, and what are these terms? This has something to do with the structure as well as the time constant. Okay. Now, as you can see here, there is a relationship. It is a relationship which is popularly known as Martin's relationship between the free surface area density and apparent density. Now, this term, A rho, refers to the free surface area density. Okay. Now, in case of a very porous structure, okay, at very low density, relative density, or in case of an open cell structure where the density of cancellous bone is very low, what happens, what has been observed, is that more the free surface area, the more is the remodeling. Okay, so this is one variable which affects or influences the rate of bone remodeling. It is basically a value, a local value of an element that can be calculated based on this relationship, mathematical relationship. And it is basically free surface area, available free surface area. Now, if the bone structure is very dense, there is not much porosity in the bone structure, then obviously the rate of bone remodeling in that zone will be very less, because there is hardly any free surface area available for remodeling. Okay, so if you see the nature of this graph, that starting from the 0 point, as you go on increasing, as the density is increasing, you can see in the zone up to say 1 grams per cc. That means up to compact bone or a cortical bone region, you can expect the free surface area density to be increasing. So this is the free surface area density A rho. Okay. The available free surface area density is increasing. Thereby, it will have a positive influence on the bone remodeling. Okay. But immediately after 1 grams per cc, you can see that the free surface area density available drastically reduces up to say this is the density of the cortical bone up to say 1.75 grams per cc. Okay. So this density up to the hardest cortical bone, in this zone, the free surface area available for remodeling is very, very less. Thereby, the influence of this parameter in the whole remodeling process reduces drastically. So this is exhibited by this relationship plotted here clearly. Just a moment. Now, how can we calculate this? Now, from the finite element model that was based on, say, a CT scan data, we will discuss that separately. So, how we generate finite element model, a detailed model with each element having a bone material property, and that is exclusively based on, a CT scan data set of a patient. Okay, I'll explain that whole procedure separately. But remember, we can actually have that data where each element, each bone element, we can have the apparent density extracted from the CT scan data set. So for a particular value of apparent density, say 0.7, for instance, 0.7 gram per cc, we can immediately calculate the free surface area from this relationship. Okay, this relationship again is a polynomial relationship, and we have used it for several simulations, and we have found we have fitted a polynomial, and we have used it for different kinds of simulations, and it works very well. It has been tested. So for a particular bone element, say 0.7, for instance, we can get a value directly from this graph. We can calculate the free surface area density and then divide it by the volume. No, it is directly, it gives you directly this arrow, small arrow. Small arrow is basically the big arrow divided by the volume of the element. And the volume of the element, of course, it can be also calculated from the FE model. So that directly gives you the arrow value. So you replace from the graph of the polynomial, you use the value of small arrow and you use that value in the main equation of bone remodeling. Now comes the time step calculation. So obviously this is a time-dependent phenomenon. Okay, where on one side you have changes in bone density, but it corresponds to certain time, another scale. Now, against time, one thing what we actually do is we can actually record or calculate changes in bone density with respect to iterations, computer iterations. The other thing is that we can relate it to some mathematical variable called simulation time steps. Okay, it is called simulation time step. But all these things, either iterations or simulation time steps, are mathematical variables. We do not know exactly that what it means in terms of physical time steps, in months or years or days, whatever. That is not exactly known in these sort of simulations. Okay? Because see, it is a simulation which is a time-dependent simulation. Now this, whether or not and to what extent it matches the actual density distribution in case of one patient, a patient, say, for instance, can be only figured out if you do a follow-up study, clinical follow-up or radiographic study of the same patient on which you are, based on which you are doing the simulations. So if there is a match of the density distribution, say after, say 4 months or 5 months or 6 months or 8 months or 1 year, maybe 1.5 years, then possibly you can relate the time step with that, with the evolutionary nature of the bone remodeling. Otherwise, it is very difficult to actually predict that what it means, what actually it means in terms of physical time step. So we initially used to predict in terms of iteration, but there is a way that we can actually convert it to simulation time step. And the simulation time step is calculated from the main equation. So you can see that you can actually have tau into delta t. One is a time constant and one is a time step. Okay, so here tau into delta t, here tau into delta t is the integration time step. Time constant can be, in total, the time constant can be calculated. So we assume that the maximum change, del rho max, is basically what can happen, a maximum change. A very low density cancellous bone may be converted to a cortical bone. So the average change is basically, say, maybe is actually half of this range of value. So it has been taken as a value. Say if we have the maximum value of cortical bone as 1.75, so the difference 1.75 minus 0 divided by 2 can be the range, that is about 0.865, something like that, or 825, something like that. So assuming that, we can also calculate this part, a rho into s minus plus minus this max. So this maximum change, what will be the total time step for this maximum change to happen? Okay. And in this calculation, you can see that this is site specific, tau constant, and this is also patient specific, site specific and patient specific. Just a moment. Now, these are small things that contributes towards the intricacy of the simulation, but grossly, you can also express it as iterations, the iterative time steps. Okay. Now, finally, what happens is that when you do this integration of the differential equations. It converts, you can actually calculate the del rho. So you have a del rho on one side integrated over del t, the time step, and you have the tau. Now this tau into delta t, this tau is a constant value. It has been predicted, or rather reported by the Wayne's group. They have assumed a value, but that is based on some experiments conducted in the lab. So over time they have observed and they came up with a recommendation of a value. And the rest is basically the theory that I have explained you. The arrow, that is the free surface area available for remodeling, and of course the difference in bone mechanical stimulus for bone remodeling. So what happens that after every iteration we have a new value of apparent density, which is designated by rho n plus 1. So the old value of rho n plus minus whatever depends on the mechanical stimulus and the difference of the remodeling stimulus. You get a new rho n plus 1. Okay, so the apparent density gets updated after every iteration, barring the condition that the remodeling or the mechanical stimulus falls within the dead zone. So within the dead zone, there is no change in the apparent density, but beyond the dead zone on both sides of the curve, remember the curve or the graph, plus minus, you have a new updated value of bone apparent density. It may be less, it may be more, but it depends exclusively on the loading conditions, on the basically the difference in the mechanical stimulus or the remodeling signal. Okay. But how long will this integration goes on? How long will it go on? So it must have a limit. On two sides, you have two limiting conditions. Is it, if it reaches a value of around 1.73, 1.73 is the value, 1.73 or 1.75 is generally the value or the apparent density of cortical bone. So this goes on until it reaches the cortical bone density. The hardest cortical bone is 1.73 or 1.75. So that is the reason I remember a value that was used for that del rho max calculation, the time step calculation, which comes out to be 0.865. Okay, the average change in the del rho max. So that comes out to be 0.865, which is half of this. Now the limits of the remodeling process, it stops at 0, about 0. So we never take 0 in computer simulation. We always take a small value close to 0. And the upper limit is the upper limit of the apparent density of cortical bone, that is 1.73 or 1.75, as the case may be. Okay. So that is the limits of the simulation. And how do you know that it has reached equilibrium condition? Obviously, it should actually, the change in apparent density should be less than a tolerance limit that you can set yourself. Okay, you can say 1% change is my tolerance. Less than 1% change in apparent density, we assume that it is hardly any change. That means we define the mathematical, it's putting a constraint in the optimization procedure, sort of. We define the equilibrium condition by defining a tolerance mathematical value which will assess the difference in subsequent values of the variable, say the apparent density. So rho n plus 1 minus rho n should be less than 1%. Okay, and then and there we consider that the process has reached equilibrium state. Okay. Now let us summarize the whole process in the form of a flow chart. Okay. So we can see many boxes here. So let us concentrate from one by one we will take. So let us start from the left hand side. Okay. We have, see here, a finite element model or analysis done on an intact femur. So this is a starting point. Okay. So you have an intact femur, the natural femur. The same model has been implanted. Okay. So same bone. So we have another one model. But the loading history is applicable, the same loading history applicable to both these models. Okay. So from the implanted model, we get the remodeling signal. From the intact model, we get the reference signal. Right? So loading history applied to the intact model gives you the reference signal. The loading history applied to the implanted femur actually gives you the remodeling signal. Then what happens is a junction. We arrive at a junction where we need to take a decision, okay, based on the range of the lazy zone or the dead zone. So we have a lazy zone or dead zone, and then we compare this difference in the remodeling signal and the reference signal, and then if it falls within the dead zone or the lazy zone, there is no remodeling straight away, and if it falls beyond the range of the dead zone, immediately it triggers bone remodeling. So first what we do is, if we consider the time step calculations, we do the time step calculation. At the preliminary level, you may not do the time step calculation. You can predict in terms of iterations. The nature of the curve, change in bone density, will actually not change, or the end configuration of the bone remodeling pattern will not be influenced by time step calculation. Okay, it is just that you will get more and more precise, points in the graph that will help you to observe the evolutionary changes in bone density during this whole process. Okay, so it just have influences. The time step has minor influence, but it actually helps you to understand more precisely that how these changes are happening. But basically, if you also consider iterations, more simpler way of predicting bone remodeling, it will not affect the end configuration, which is very important for us, right? The final equilibrium configuration of bone density, how bone density has changed after implantation. Okay, that configuration will, whatever way you predict, has to be same. Oops. Yeah. So we do the time step calculation and then we apply the remodeling rule. As you can see here very clearly, we apply the remodeling equations. So when we apply the remodeling equations, it triggers change in bone density, which triggers change in elastic modulus. Okay. And immediately we get a new structure, bone structure, which needs to be solved again using the applied loading condition. The moment the apparent density of a bone element changes, oops, the apparent density of a bone element changes, it changes the elastic modulus by the power law relationship that we have used while generating the FE model, and a completely new finite element model of the bone structure along with the implant evolves, which needs to be solved again. Okay, so again and again until it reaches the equilibrium condition. So that is where you keep on iterating. So this whole process, as you can see, designated by the box, rectangular box, keeps on doing the simulations for me, and then it comes up with the final configuration of bone density pattern after attainment of equilibrium. Now, just to show you how things are, this I will cover it separately, but how this simulation is done. Just to show you, the starting point is CT scan data. So CT scan data is processed. As you can see here, this is a pelvic bone model. So from CT scan image processing, we use the layer reconstruction method of the CT scan data, and then we generate a solid model of bone. Okay, so from solid model to finite element model. Okay, so image processing of CT scan data slices or data set. Then when we have this finite element model, we actually do linear calibration of the CT gray values with apparent density. So this can be done. There is a procedure of doing it. We based on two values. One is non-bone condition, maybe water, fat, other bone marrow. It has a value generally around CT gray value of around 0. Okay, and the cortical bone, we know the density value of the cortical bone, so we flush it with we calibrate this bone apparent density with these two end conditions, and we set up a linear equation based on which we can actually get apparent density of any bone element. And once we have the apparent density, we can use the power law relationship to find out the elastic modulus. Cortical bone elastic modulus is generally, the maximum. It is about 17 gigapascal, whereas in the cortical bone zone, it will be around, say, maximum 3000 MPa. Okay, remember, so there is a gross difference huge difference between the modulus of cortical bone and cancellous bone. So finally, we have a FE model where each bone element is assigned individual material property based on CT gray value of the CT scan data set. So in this case, it has almost about 2.21 lakh, about 200,000. So that means 2,22,000. Okay. So we give the applied loading condition. We have, say, for instance, the hip joint reaction force, 21 muscle forces, and the physiological constraints that are available, fixed boundary conditions, and the pubis and the sacroiliac joint. So this is the pubis and the sacroiliac. This is where another pelvic bone meets the right side. Okay. So this is the hemipelvis. The other pelvis meets this bone here at the pubis. And the sacroiliac joint is the joint at the sacrum. So we take in this gait cycle two load cases, for instance, that is designated by the red points in the graph. So we get a principal stress distribution of the hemipelvis. Load case 2, beginning of right single support case. This is where we have the maximum hip joint reaction force during the gait cycle. Okay. So what is the stress distribution within the bone corresponding to this load case? Fully loaded with muscle and hip joint reaction force. You get the first principal stress distribution, you get the third principal stress distribution. A detailed stress analysis of the bone during a walking cycle, gait cycle, you can obtain. This is so powerful. Then we actually do all these tricks that is applicable for aerospace modeling and analysis. We put the acetabular component, virtual implantation, generate a FE model. We generate a submodel. You see, the submodel is a much finer model compared to the whole model, okay? Because we are interested more in the domain of inclusion of the prosthesis. So the maximum change of bone density will occur in the neighborhood of the inclusion of the prosthesis. As you go far away from the acetabulum, the changes is assumed to be less. Okay. Therefore, we have a truncated model, but we actually include the elastic behavior of the remaining portion of the pelvic bone by transferring the nodal displacements at these cut boundaries from the full model. Okay. In this way, this is a solid mechanics trick by which we can actually a technique which is popularly known as the submodeling technique. This is also, as I told you, used in aerospace structure, where you may be interested about one portion, say the wings or the tail. It's a critical part. So you can do a truncated analysis, a submodeling analysis by using the submodeling technique. But you need to also include the elastic behavior of the rest of the model. And through this method, using this method, it's a very efficient way of doing a model. And you can see when you compare the full-scale model with the submodel, what is the difference? There's hardly any difference. Now, when we have a submodel with very fine mesh, obviously the material property distribution in that model is much more precise than the full-scale model, which actually has larger elements. Okay. So any subtle change in the material property distribution will be reflected in the submodel. And whatever changes that you see, whatever differences that you observe between these two results, this is the same stress distribution results, so the full-scale model and the submodel, is due to that subtle difference in material property distribution. Okay? But you see, it agrees. It is so nicely, it has come up. This is published in one of the top journals. This technique and the way we have applied it in the evaluation of stress analysis has been very well appreciated. Now, if you see what are the changes in bone distribution using a metallic or a ceramic implant in case of acetabular prosthesis, immediately the results are in front of you. So you have immediate postoperative, which is same as you see the starting point of the bone remodeling simulation. It is basically the density configuration which with you start. And in this, it is same as what the patient had before surgery. Okay. With time, you can see an implant which is assumed to be fully bonded at the interface. You see the changes. How much bone has disappeared due to bone resorption in case of a metallic and ceramic implant. This is a fully bonded case, the interface. A partially bonded or debonded implant, this is an interface condition that also has influence because it changes the stress strain distribution. There also you see, quite a change. There is bone apposition on the periphery. If you look very carefully, compare the figure on the left-hand side and compare each figure on the middle and the right-hand side. You see that bone density has increased near the periphery of the acetabulum or acetabular prosthesis, whereas in the central region, bone density is decreasing. Okay, so a progression of the curve in different region, is shown here in this curve, where the time tau into delta t is designated as the simulation time step. We do not know what is exactly the physical, it means in terms of physical time step. See how powerful is our analysis. We can actually evaluate different kinds of prosthesis designs. Okay, so in this case, a Cambridge cup or a Mitch cup, or this is Mitch cup, this is the Cambridge cup design which we have been used. So we have Mitch cup, we have Cambridge cup photos here. And you see, we take a hypothetical cup, say with 3 millimeter full. You see there is a horseshoe cut here, there's a horseshoe cut here, but there is no cut on the right hand side, prosthesis 3, which is purely hemispherical. Now how these, stiffness, changes in stiffness, design, thickness, whatever, translates into bone remodeling. So changing in bone density around these composite cups, immediate post-operative is same as earlier. For prosthesis 1, you see so much of change because prosthesis 1 is thicker. If I go back, just allow me to go back. So this is 3 millimeter ultra high molecular weight polyethylene bearing surface. It has a backing of 1.5 millimeter thick CFR PVT. So total thickness of the cup is 4.5. If it is a 3 millimeter CFR peak cup, it's a Mitch cup, and 3 millimeter hemispherical cup. So this is a thicker acetabular cup, and these are thinner acetabular cup. So obviously the stiffness will change, and thereby the stress strain distribution. So this is prosthesis 1, where you can see a thick Cambridge cup, and if you compare prosthesis 1 with prosthesis 2 or prosthesis 3, you immediately see the difference in the bone remodeling patterns. So more bone resorption within the central zone of the acetabulum as compared to prosthesis 2 and prosthesis 3. Again, if you compare prosthesis 3 with prosthesis 2, the effect of the stiffness due to exclusion and inclusion of the horseshoe that cut is evident. This has the least stiffness as compared to prosthesis, all these 3 prosthesis design. This is a fully hemispherical cup, and this is a hemispherical cup with a cutout. And you can see the difference immediately. So, if you look into several sections in bone density, the bone density for CFR peak implant, you can see immediately that how this bone remodeling is affecting the bone structure. Okay. Post-operative section 1, 2, 3, as you can see here. So the locations of sections 1, 2, 3. Okay. Now for a 3 millimeter thick implant, you can see the changes very clearly. So bone is disappearing. So bone is disappearing. Bone resorption on the left side, okay, particularly in section 2 and section 3, not much in section 1, okay, which is the top section. In case when it increases to 11 millimeter thick implant, say polyethylene implant, then what happens? Huge bone resorptions. You know, bone resorption is predicted in section 2, section 3, even in section 1. Okay. So the major findings are, for the analysis of the pelvic bone, the effect of stress shielding was observed at the central part of the acetabulum, whereas a pronounced strain increase was observed around the periphery of the acetabulum. So the effect of stress shielding, as I had told you, the phenomenon of stress shielding that leads to bone remodeling, that the bone element doesn't receive enough stimulus as it was receiving in case of an intact situation. Okay, so the mechanical environment, the change in mechanical environment in the implanted situation is very much evident due to the effect of stress or strain shielding. So strain shielding was considerably higher for the bonded. So these are more intricacies. So different interface condition, different, it leads to different stress strain results. Changes in design leads to changes in bone remodeling patterns. So you can see here that horseshoe-shaped CFR peak appears to be a better alternative bearing surface than any other designs regarding strain shielding, bone deformation, and bone remodeling. So this is, you can make the decisions about the design, a particular design, based on these predictions. And thickness of the acetabular component played a crucial role in the implant-induced bone adaptation. Okay? I can continue. I have to stop here because I can show you more slides, but I will stop here because it's more than an hour now that I have been talking. Okay. Just a moment.